Welcome back, everybody. In this lecture, we're going to continue on chapter 24, and we are going to discuss further what we mean by magnetic field in a more quantitative way, and we're going to describe a little bit of what that means. So what we tried to describe last time, and as discussed in your book, electric currents generate magnetic fields, electric currents. So anytime I have a circulating charge in a loop, for example, that will make a magnetic field that looks very much like the magnetic field of a bar magnet. If, on the other hand, I have an electric current which is in a straight wire, such as what you see here, it will also generate a magnetic field. We're going to use the notation that the letter B is going to be used to indicate what we mean by the strength of the magnetic field, just as the letter E denoted the strength of the electric field. Now, you recall that the electric field strength was related to the force by multiplying this electric field by the charge that's experiencing the electric field. And so, similarly, we will have a case where we will have a magnetic field that is going to generate or be related to a force on a moving charge. And that's what we'll find in just a short while. So magnetic field forms a pattern of concentric circles around a current wire. The idea that we're expressing here, and this is something that is going to be new for you, is that I can imagine that there's a voltage supply that is generating current in this wire. And when I get current flowing through this wire, what the laws of magnetism tell us is that it will generate a magnetic field that circulates around the wire, and it becomes weaker as we go to a larger radius. But if we were to throw iron filings, or in this case, compasses, little bar magnets, on the surface of a piece of paper that's perpendicular to the wire, then what we see is that each of these compass indicators, which are themselves little tiny bar magnets, would align themselves in a pattern that forms a circle going around here and tells us that therefore the direction of the magnetic field is in a circular pattern around the wire. Furthermore, one can show that if we now send electric current going the opposite direction, say from the top to the bottom, that the directions of these bar magnets will spin 180 degrees, and they will now indicate for us that the magnetic field is circulating in the opposite direction. For example, when the current in the wire is going vertically up, I can use what's called the right-hand rule. My thumb points in the direction of the current in the wire, and my fingers, in using the right hand, show that the direction of the magnetic field wraps around the wire. And that indicates the direction of the magnetic field. The strength of the magnetic field, which is to say how strong the field is or how strong the force will be on a moving charge, is going to be given by some constant times the current I1, which is in the wire, divided by the radius of the wire. So what this tells us is that there's two ways to increase the magnetic field. I can either increase the current, or I can look at examine a point closer to the wire, which is this distance r. So r is the distance from the center of the wire to, in this case, for example, the distance to the compass on the table. That distance, radial distance r, it will be an indicator of how strong the magnetic field is. And this will, of course, then dictate to us how to calculate as well what the strength of the magnetic field is going to be. So this is a way of visualizing the magnetic field that is produced by a current of wire. And what we've said here is that if I have a current going from left to right, a positive current of electricity going through the wire from left to right, then using the right-hand rule, the magnetic field will curve in circles around the wire given by the direction of my fingers in the right-hand rule with my thumb pointing in the direction of the current. If, on the other hand, I now make a loop within that wire, then the magnetic field far from the loop will in fact be the same. It sees a straight section of wire. But in the region where the wire begins to make a curved circle, then they still will make these circular magnetic field patterns around the wire. But now, taken as a whole, what one can see is that there is more magnetic field as you move towards the center, because all of these loops of magnetic field are reinforcing each other as we move towards the middle. This simply shows you that the magnetic field always follows perpendicular to the direction of the current, and it's perpendicular to the wire itself. So, magnetic force between two straight current carrying wires. This is the direct analogy of what we have as the attraction between two opposite charges that are sitting very, very close to each other. If the two charges are opposite, they are going to attract. If the two charges are of the same sign, say both charges, and we're talking about electric fields, are of the same sign, then they will repel each other. And we have a similar phenomena with magnetism, but it works slightly different. So imagine that one current carrying wire produces a circuit. Well, one current carrying wire has a circular magnetic field around it. Now, a second wire with an equal current will be attracted to the first wire, since it feels the magnetic field of the first wire. And this is where we get into how we translate between magnetic field and magnetic force. So the field is generated by those blue lines we saw, but the force is actually perpendicular to those fields, because it is due strictly to the motion of the charges in the second wire. So a second wire with an equal current will be attracted to the first wire, since it feels the magnetic field of the first wire. And Biot-Savart came up with a formula for the law of attraction between two such wires. And basically what they were able to show was that the force of attraction was given by the product of the charges on each of the wire. Now, initially what I had told you is that the wire in the second wire was the same as the first, so that meant that I1 is equal to I2, and that can in fact be the case, but as you can see here, it doesn't have to be the case. But the force between the two wires is going to be given by the product of the currents divided by the distance between the centers of the wire. So as the two wires get further and further apart, the force of attraction decreases. Note the similarity with Coulomb's force law for two charges, Q1 and Q2, the difference being that force drops off like 1 over r squared, whereas this one drops off only as inversely as the distance between them, instead of inversely as the square of the distance between them. That means that it does not fall off as quickly. But they both depend on product. One of them is on charges and one of them is on current. And therefore, we see here is that the force, the magnetic force, only becomes visible as a force when there's charge moving in the wire. And that movement of the wire is designated by this quantity called the current. We can demonstrate this also by using an external magnet which has its own magnetic field. And in this case, what we observe is that if we pass a positive current, and to do my right-hand rule here, if I put a current traveling in the direction given by the arrow, then the wire initially located at the position of the dotted line, as we add current, gets pushed in the upward direction. And if the current is reversed, so that initially we have no current at all, it's strung right between the north and south pole of the magnet, then we have that when we apply the current in the opposite direction, it gets pushed down with the same force as it did in the case where the current was reversed, but it's pushed up in the other direction. And what this rule tells us, or what this observation tells us, is that we now know how to calculate a magnetic force based on the magnetic field that is created by the magnet. And the way we express this is to say that the force on the wire depends on the magnetic, how strong is the magnet, times how much current is flowing in the wire. So the higher the amount of current in the wire, the more upward force there is, in the case on the left. Or if I increase the magnetic field, that will also increase the force on the wire. So the idea is that you think of this current wire as being stretched with a certain tension, although it does have some looseness to move up or down so that we can observe the deflection as we apply current through the wire. Now, another way to describe this is by using what we call the vector cross rule. And basically what the vector cross rule tells us is that we know if this was a north pole on the right here and a south pole on the left, and the field lines go from north to south, then the velocity or the charges are moving with the velocity in the direction of the wire. And therefore, if I take my right hand and the lower base of the right hand, I curl my fingers from the vector direction of the current towards the vector direction of the magnetic field, then the resulting direction of my thumb gives me the direction of the force. And that's a case where the direction of the force is perpendicular to the magnetic field lines and to the current of the wire itself. And that is exactly how we express the force law in terms of the magnetic field. It's strongest when the current is perpendicular to the magnetic field lines, and it's weakest when the current is parallel to the field lines. So it definitely depends on the directionality between the current and the magnetic field. In this case, the current is perpendicular to the magnetic field, which gives us the maximum deflection. Well, that's a lot to pack into a single slide, but it's important to make the connection between what we mean by magnetic field and what we mean by the magnetic force on a wire, which is the force on charges that are moving in a magnetic field. There are a number of ways we can create magnetic fields from current carrying wires. We discussed the one on the left where if we apply a current through a long wire, as you see here, and I lightly sprinkle some filings on the paper around the wire. The wire is going above and below the plane of the paper, so there's a long line of current below the paper as there are as above. You only see the bar above the line, above the plane of the paper, but there's also one coming from below. But if I throw these filings gently along on the piece of paper, the little tiny bar magnets of the filing will line up in north and south in a circular pattern, just as the compasses did, and we can see the effects or the pattern of the magnetic field that's produced from a straight line of current flowing through a wire. Another way to increase to make a stronger magnetic field, or to make a magnetic field that looks very much like a bar magnet, is, and here you'll see the similarity with the Earth's magnetic field shape right here, is that imagine that instead of one loop of current, such as I have in the middle figure here, with the field lines making circles around the wire, I have now 6 loops of current that are all tied together, passing the same current through all of them. And now what I see is that, throwing filings on the sheet of paper, that the magnetic field goes in a direction that is fairly uniform in the middle of all of those loops, and then diverges out the end, and then they come back and circle back into the bottom of the set of loops. So this gives you a magnetic field that looks very much like a bar magnet. In fact, it verifies what we have said, is that the magnetism itself is created by the movement or the spinning of charges around the atoms, and those spinning charges create currents, which then generate magnetic fields that look very much like we see in the bar magnet. Electromagnets, how to make a stronger magnetic field. So one of the ways we might want to create a very, very strong magnetic field is to place an iron bar in a current carrying coil. You can do this as an experiment at home with your kitchen supplies. You go to the hardware store and buy an iron nail, and get a nail that is composed mostly of iron, very commonly found in hardware stores. Wrap the wire, the nail, which is a very long bar shape of iron, wrap it with insulated wires that wrap around the nail many times, and at both ends of the wire that have wrapped around the nail, what you do is attach a battery, and the battery then will cause the current to flow, and the current that flows will look very much like the current through these copper windings right here, which we only have 6 of them, but it'd be very easy to make 100 or 1,000 windings, and you can make it very much a much stronger magnetic field. And you place a piece of iron right in the middle of this. And what happens now is that we not only get the magnetic field due to the current of the wire creating through here, but we align all of the domains within the iron magnet or bar itself, so that we get the sum of the magnetic field of the iron plus the magnetic field due to the circulating charge of loops of charge that is created by the wire. So the field of the coil will align the magnetic domains in the iron to reinforce the coil's magnetic field, making the total field hundreds or even 1,000 times stronger than you would get using only the coil of electricity. So the iron reinforces. But furthermore, most other important also is that by changing the current, I can also control the magnetic field coming out of the ends of the bar magnet. And that can be very useful when we need to have a user's selected magnetic field. And that can be controlled by the amount of current I send through it. So we call this device, if I imagine this picture with a bar magnet going through the middle, we call this device an electromagnet. And this is a very useful device for numerous types of applications. Magnetic forces on moving charges. So we've talked about this already a little bit. The current through the wire is due to the movement of charges, and as a result, those moving charges will feel the effects of a magnetic field located outside the wire. And also, the magnetic force is perpendicular to the direction of the velocity of the charges as well as the magnetic field. So moving charges in a magnetic field will experience a deflecting force. And we've shown that in the picture with the wire that got deflected in the U-shaped magnet. It will be the greatest force when the electric charge movement is in the direction perpendicular to the magnetic field lines, and it will be least when the charge movement is parallel. That's to say, that's the case where there's actually no force, when the charge movement is parallel to the magnetic field lines. So we only get a magnetic force when there's a component of the velocity that's perpendicular to the magnetic field lines. And then we can see the magnetic force. Another way to experience or show the effect of a magnetic field on a movement of charged particles is to imagine that we have a beam of electrons. We are able to ionize or liberate electrons from the tip of a heated piece of metal, and we can accelerate them with an electric field, make them go to very high velocity, and then pass them through a magnet. And as we do so in this case, what will happen is that due to the velocity of the charge going through the magnetic field, it gets deflected upwards. And that upward deflection is caused by this right-hand rule that we talked about, which was the cross product of the velocity vector and with the velocity vector and the magnetic field vector. So V cross B, V is pointing in the direction coming right through the magnet. The field lines go from north to south. The force becomes a vertical, which is perpendicular to both the horizontal field line from north to south, as well as the horizontal velocity vector. So moving charges in a magnetic field will experience a deflecting force. And this is actually how we can steer beams of electrons through different objects. In the old-fashioned television sets, the electron beams were generated in the back of the tube of the television, and it passed through a magnetic field, which was controlled very precisely to sweep the beam across the illuminating the fluorescent screen that then gave us the picture that we saw on the early television sets. Another application of the interaction between current-carrying wires and magnetic fields is an example where we can use magnetic properties of the coils of wire and the magnetic properties of a bar magnet our compass, which is nothing but a bar magnet with pivoted on the center so that it can spin. We can place this compass bar magnet inside multiple loops of current, and when we do that, then we get that there's a magnetic force which will cause the bar magnet to spin about its central axis. And the amount by which it spins will be proportional to how much current is going through the wire. So by measuring the deflection of this bar magnet, we can use this as an example, determine how much current is going through the wires. So the current through the wires creates a magnetic field. The magnetic field interacts with the bar magnet. The bar magnet then, which is the compass itself, the needle begins to turn, and as the needle turns, we measure that we are directly measuring the current that goes through all these coils. So the compass rotates to align with the B field of the current, and in this case, as we know from loops of current, the B field will circulate through the middle and out around the edges and then circle back in again. So this is the idea of, a primitive idea of the starting point of how we would create a device that can measure current. Okay, so we started talking about the idea of a measurement device that can measure current in a loop or in a circuit. So what I'm going to do here is draw for you a simple diagram of a very simple circuit which has a battery, a resistor, and in the middle I'm going to have a device to measure the current. And that is what this upper portion is about. Now we know from Ohm's law that the current that is flowing through this will be given by V equals IR. So because of the fact that the voltage is 12 and the resistance is 2, then we get 6A, or what we call 6 amperes. So the amperes is the unit of electric current. Now we may want to verify that, measure that, and verify that in fact we do get 6 amps of current. So we have a device called an ammeter. That's short for amp meter or ampere meter, but that's a meter that measures amperes, or current. And so the basic idea of that is what's called a galvanometer, which is what we will show when we go back to the slides. But I've drawn a picture of it for you right here, where I make a small excursion of the current going from the battery to the resistor by going up through a loop that is illustrated in the black lines. And the current goes through a loop and then goes back into its normal path through the circuit. Now as a result of this, the current is passing through an area where there is a magnet here. And the tendency of the magnet will be to twist the loop about its post. So there's a post here that is more or less fixed that allows the force or the loop to rotate in the magnetic field. And the reason it's going to rotate is that this leg of the current has its current or charge moving in the upward direction. The magnetic field is moving from north to south, so the direction of the force will be to push this leg of the loop into the board and to pull this leg of the loop out of the board. And that provides what's called torque. And that torque will cause this whole loop to rotate. Now as this loop rotates, it will be attached to a needle that points to an indicator of amperes, right? So we will have amperes going. We might assume, for example, this could be 0 amps over here, this would be 6 amps over here, and in between would be 3 amps in the middle. So by looking at where the needle arrives from the dial, we have determined that, or gotten that information by how much this loop of current was twisted in the magnetic field, causing the needle attached to it to move either to move in the direction of the rotating coil. So this is how we can measure the current, and that whole thing takes place in a device that encircles the what we would call this whole device being the ammeter that gets placed inside the circuit in order to measure the current. So this shows you how to measure current from the interaction of the magnetic field with the current that's going through it, and we can use this interaction to actually tell us how much current is going through the loop by how much this coil gets twisted and deflected as it is experiencing the magnetic field. And the resulting amount of twist on that coil will tell us how many amps or how much current went through there. Okay, so I'm going to stop at this point on this one. We'll go back to the slides, and then we'll finish up, and I can show you what we have in the remaining. Okay, so we're going to finish up this chapter by talking about the electric motor. The electric motor is another example of how the current through a wire interacts with a magnetic field, and we can use this interaction to generate what we call the spinning motion. And the spinning motion can be used to drive a mechanical device, such that as wheels on a toy car or anything that requires rotational motion. So the basic idea is that I have a magnet that generates a north and a south field, and the loop of wire is passing through the bar magnet itself. And in two legs of the loop, which is the one on the bottom and the one on top, the magnetic field will generate a force that is pushing this upper arm of the loop in towards the North Pole, pushing the lower leg of the loop towards the South Pole, and that causes a rotation to actually spin the loop inside the magnetic field. And the other important factor of this is that every time it reaches the top of when it reaches the point where the area of the loop is passing right through the magnetic field, the direction of the current reverses itself so that the rotation will continue to go in the same counterclockwise direction indicated by this arrow. And so every half rotation, the direction of current changes, that will then reverses itself so that the forces acting on the wire are such that it keeps it rotating in the same direction. Now this takes kind of an involved analysis to go through all the steps, but the basic idea is that the current in two legs of this loop, the upper and the lower, have a force exerted on them by the magnetic field, which causes it to spin and twist about its axis in the direction shown. And as a result, one can make continuous rotation if there, of course, is a battery, a force, a power source, electrical power source, capable of maintaining that current in such a way that as long as this is maintained, I will continue to get the rotational motion, and that will happen until the battery runs out of its net amount of charge capability, which we said last time was measured in amp hours. So the whole idea of this is that a charge moving through a magnetic field can be used to generate a mechanical spinning motion to drive other objects as one needs. So we'll stop right there, and when we resume, we'll go into chapter 24 to 25.